Following on from basic aerodynamic theory, this lesson on subsonic airflow will cover the principal definitions and terminology concerning aerofoils and the airflow around them, and how changes in airflow affect the resultant forces. The aerofoil can be defined as a shape capable of producing lift with relatively high efficiency. As air flows over an aerofoil at a sufficient speed, it will have certain effects on the static pressure surrounding the aerofoil, as propounded by the principle of continuity and Bernoulli's theorem in the last lesson. Even before the airflow reaches the aerofoil, the pressure drop over the upper surface will cause the flow to rise towards it. This is known as upwash. At a point on the lower side of the leading edge, the airflow will be brought to a halt at a point called the stagnation point, where the airflow separates to pass over or under the wing. As the air flows back over the aerofoil, it will tend to slow down in accordance with the basic principles, flowing against the adverse pressure gradient as the higher pressure air below the aerofoil tries to go from high to low pressure, that is, forward from the trailing edge to the low pressure area on top. The pressure distribution is shown here, with the highest pressure concentrated around the stagnation point, and the low pressure extending up and forward to a peak above the aerofoil, with the pressure differential creating the lift force indicated. Also shown is the force, drag, which acts against the forward movement of a wing and is caused partly by the lift itself. Lift and drag are fully covered in subsequent lessons in the syllabus. Having introduced the basic characteristics of the airflow around an aerofoil, we shall now look at the terminology and definitions associated with aerofoils. The chord line is a straight line joining the centers of curvature of the leading and trailing edges of an aerofoil. The chord is the distance between the leading and trailing edges, measured along the chord line. The angle of incidence is the angle between the wing root chord line and the longitudinal axis of the aircraft. This is fixed for the wing, but may be variable for the tailplane. The mean camber line, also known as the mean line or camber line, is a line joining the leading and trailing edges equidistant from the upper and lower surfaces. Maximum camber is the greatest distance of the mean camber line from the chord line, and is expressed as a percentage of the chord, and its location along the chord line as a percentage of the chord measured from the leading edge. When the camber line is above the chord line, the aerofoil is said to have positive camber, and when it is below, negative camber. A symmetrical aerofoil has no camber, as chord and camber lines are coincident. Thickness-chord ratio is the maximum thickness or depth of an aerofoil section expressed as a percentage of the chord from the leading edge. The thickness and thickness distribution of an aerofoil section have a significant effect on its airflow characteristics. Leading edge radius is the radius of the curvature of the leading edge, which can significantly affect the initial airflow characteristics of the aerofoil. Basically, the smaller the radius, the sharper the leading edge. Relative airflow, or relative wind, or free stream flow, is the direction of the airflow produced by the movement of the aircraft through the air, and has three characteristics. First, its direction is opposite and parallel to the flight path, which is the direction taken by the center of gravity. The aircraft's attitude is not a factor. Secondly, its condition is that it is air close to but unaffected by the presence of the aircraft. That is, its temperature, pressure and velocity are not changed by the aircraft's passage through it. Thirdly, the relative airflow's magnitude is the speed of the aircraft through the air, the true airspeed. If the airflow does not possess all of these three characteristics, it is referred to as effective airflow. Total reaction is the resultant of all the forces acting on the aerofoil section, namely lift and drag. The center of pressure, or CP, is the point on the chord line through which lift is considered to act. Lift is the aerodynamic force generated by the aerofoil, which acts at 90 degrees to the relative airflow. Drag is the aerodynamic force which acts parallel to and in the same direction as the relative airflow, that is, opposite to the flight path. Angle of attack is the angle between the chord line and the relative airflow. It is often referred to as alpha, written as the Greek letter. An alternative, but less used term is aerodynamic incidence. The angle of attack between the chord line and the effective airflow is referred to as the effective angle of attack. When we are considering airflow velocity, it makes no difference to the pressure pattern created by the flow over an aerofoil if the aircraft is moving through the air or the air is moving over the aircraft. It is the relative velocity which is the most important factor. For example, an aircraft flying level at 80 knots will produce about the same lift as it would stationary on the ground, facing into an 80-knot wind, depending on angle of attack. To promote full understanding, we will be referring to both situations, either where air flows over a wind tunnel model, or aircraft in flight moving through stationary air. Three-dimensional airflow is the true airflow over an aircraft and consists of a two-dimensional flow, modified by various pressure differentials. This will be examined later in the syllabus. For now, we will consider two-dimensional airflow. Two-dimensional airflow assumes a wing with the same aerofoil section along its entire span, with no span-wise pressure differential or flow. This concept is used to illustrate the basic principles of the generation of aerodynamic force. As air flows towards an aerofoil, it will be turned upwards towards the lower pressure over the upper surface. This is termed upwash. After passing over the aerofoil, the flow returns to its original flow level and state. This is termed downwash. On the screen, you can see an aerofoil at a representative angle of attack, subject to a given dynamic pressure or IAS. The pressure distribution showing that if the static pressure on one side of a body is reduced more than on the other side, a pressure differential will exist. If the same angle of attack is maintained, and the IAS, and thus the dynamic pressure, is increased, the pressure differential will increase. The pressure differential acting on the surface area will produce an upward acting force. So, if dynamic pressure increases, the upwards force increases. At a constant dynamic pressure, increasing the angle of attack, or alpha, will also increase the pressure differential, but will also alter its distribution pattern. The aerofoil profile presented to the airflow will determine the distribution of velocity change, and hence the pressure pattern over the surface. This pattern is determined by the aerofoil's geometry, that is, the thickness and its distribution, which are fixed, the camber and its distribution, which are assumed to be fixed for now, and by the alpha, which is variable. The greatest positive pressure occurs at the stagnation point, where the relative flow velocity is 0. This point is somewhere near the leading edge. As the alpha increases from -4, it moves from the upper surface around the leading edge to the lower surface. The stagnation point is where the airflow divides over the upper and lower surfaces, and pressure here is static plus dynamic. The flow over the top accelerates rapidly around the leading edge and over the front portion of the wing, creating a substantial static pressure drop. The rate of acceleration increases with alpha, up to about 16 degrees. The pressure reduces continuously from stagnation value, through free stream pressure, to a position on the top surface where a peak value is reached. From there, the airflow decelerates progressively, and the pressure rises back to free stream near the trailing edge. It should be noted that any imperfections on the upper leading edge surface, such as dents, dirt and insects, ice or frost, etc., can seriously disrupt the flow acceleration in this critical area. At alphas less than 8 degrees, the underside flow is much less accelerated and reduces pressure to only a small negative value. The pressure differential between the stagnation point and the lower pressure at the trailing edge creates a backwards acting force called form or pressure drag, which is covered later in the syllabus. We can now examine what happens to the pressure pattern as the angle of attack changes, starting with low angles. With an alpha of -4 degrees, the drop in pressure is the same above and below the section. There is no differential, and therefore no lift. This is known as the zero lift angle of attack. At 0 degrees alpha, there is a pressure decrease over the upper surface compared with free stream flow, with a smaller decrease on the underside. Even at small angles of attack, between -4 and 0, a positively cambered section will produce lift. The positive pressure at the leading edge is dynamic, or in this context, stagnation pressure. As angle of attack is increased, here to around 4 degrees, the lift force is increased because of the greater acceleration of the upper surface flow in the reduced cross-sectional area of the local stream tube. The low pressure peak moves forward as the angle of attack increases. At 8 degrees, the peak is higher and further forward, and nearly all the lift is from the upper surface. But the increased frontal area means that stagnation pressure is adding to the rearward force. At about 14 degrees, the low pressure peak is well forward, and the high pressure area under the wing is greater, adding to both lift and drag. The contribution to the rearwards force is due to the pressure gradient, which is a change in pressure over distance. The greater the pressure difference, the steeper the gradient. As air tries to flow from high to low pressure, a favourable gradient is one in which the pressure is falling in the direction of the airflow. And an adverse gradient is one in which it is rising in the flow direction, such as between the point of minimum pressure over the aerofoil and the trailing edge. The gradient increases with angle of attack. As the angle of attack reaches about 16 degrees, the adverse pressure gradient is such that the air is trying to flow forward from the trailing edge against the airflow, preventing the previously smooth streamline flow from following the surface of the aerofoil, and causing the low pressure area over the upper surface to collapse suddenly. Any pressure differential remaining is due to the pressure increase on the underside only. This condition is known as the stall, described fully in a later lesson. The whole surface of the aerofoil contributes to lift, but the point along the chord where the lift is effectively concentrated is termed the centre of pressure. The location of the centre of pressure, or CP, is a function of camber and lift coefficient, which depends partly on angle of attack. As the alpha increases from 0 to 16 degrees, the upper peak of low pressure, or suction, will move forward, taking the point of concentration of lift, the CP, with it. The magnitude of the lift force also increases with alpha, until the stall is reached, at which point the lift force decreases abruptly, and the CP moves back along the chord. Note that the CP is at its most forward point, where lift is at its maximum, just before the stall. A coefficient is a number without unit or dimension, expressing a degree of magnitude. An aerodynamic force coefficient is a common denominator for all aircraft, regardless of weight, size or speed, and is a ratio between the average aerodynamic pressure and the airstream dynamic pressure. By this definition, a lift coefficient, or CL, is the ratio between lift divided by wing planform area, or lift pressure, and dynamic pressure. A drag coefficient, CD, is the ratio between drag divided by wing area and dynamic pressure. As speed increases, Assuming a constant density, CD will remain constant, since drag pressure and dynamic pressure are increasing in the same proportion. We need to use coefficients of aerodynamic force, as they provide an index of the force, independent of area, air density or velocity, being derived from the relative pressure and velocity distribution. They are influenced only by the shape of the surface and angle of attack, since it is principally these factors that determine the pressure distribution. The last section of this lesson covers aerodynamic pitching moments. To refresh your memory, a moment is defined as the product of a force and the distance through which it acts. In the case in which we are considering the moment, it is purely a leverage, and no movement is involved. The distribution of pressure over a surface is the source of aerodynamic moments as well as forces. There are two ways of considering the effects of a changing angle of attack on the pitching moment of an aerofoil. Either by measuring the changes in magnitude of lift through a moving centre of pressure, or, more simply, through a fixed aerodynamic centre. You know from the previous parts of this lesson that as the angle of attack increases, the CP moves forward and the magnitude of lift increases, and vice versa. This results in a changing force with a changing point of application. The aerodynamic centre, or AC, is a fixed point on the chord line, and can be defined as the point where all changes in the magnitude of lift effectively take place, and the point about which the pitching moment will remain constant at normal angles of attack. For subsonic airflows of less than Mach 0.4, the AC is located at the 25% chord point, regardless of camber, thickness or angle of attack. The AC is an aerodynamic reference point, which is used for examination of the theory of incompressible airflow, and is most directly applicable to longitudinal stability, as you will see later in the syllabus. There is a nose-down pitching moment about the AC, which is a product of the lift force at the CP and the arm between the CP and the AC. Since an increase in alpha will not only increase the lift force, but also shorten the lever arm as the CP moves forward towards the AC, the moment about the AC remains the same at any angle of attack within the normal flight range. With a symmetrical aerofoil at 0 alpha, the upper and lower forces are equal and symmetrically distributed. With an increasing angle of attack, the upper surface force increases and the lower force decreases. A change in the magnitude of the lift forces has taken place without a change in the position of the centre of pressure, which is a characteristic of symmetrical aerofoils. Thus, the pitching moment about the aerodynamic centre will be 0 at normal angles of attack, which is one of the big advantages of such aerofoils. To summarise the significant points of this lesson, we can start with the main things affecting airflow pattern, and consequently lift and drag. It will depend on angle of attack, airflow cross-sectional area change, aerofoil shape, that is, thickness and camber, again, airflow cross-section, air density, air mass flow decreasing with greater altitude, and velocity, air mass flow, changing with TAS. The lift force is the result of the pressure differential between the upper and lower surfaces of an aerofoil. The greatest contribution comes from the top surface. Any contamination, particularly ice, or deformation of the upper leading edge surface can seriously disrupt the airflow acceleration, and hence the magnitude of the lift force. An increase in dynamic pressure with indicated airspeed will increase the lift force, and vice versa. An increase in angle of attack, alpha, will increase the lift force, and vice versa, over the normal flight range of 0 to 16 degrees. The centre of pressure of a cambered aerofoil moves forward as alpha increases, whereas the CP of a symmetrical aerofoil does not, within the normal range. Throughout the normal alpha range, the aerofoil's pitch-down moment about the aerodynamic center, or AC, will remain constant. The AC is at the quarter chord position for subsonic flow of less than Mach 0.4. The coefficient of lift is the ratio between lift per unit wing area and dynamic pressure. As alpha increases from -4 degrees, the leading edge stagnation point moves from the upper surface around the leading edge to the lower surface. The greatest positive pressure occurs at the leading edge stagnation point, where the relative flow velocity is 0. Form or pressure, drag, is the result of the pressure differential between the leading and trailing edges of the aerofoil. An increase in dynamic pressure, that is, indicated airspeed, will increase form drag, and vice versa. The coefficient of drag is the ratio between drag per unit wing area and dynamic pressure.